In our previous video, we have understood the in-depth maths intuition behind linear regression. And we found out that, okay, we really need to find out the best fit line. Along with that, we also saw what is the equation of the best fit line. H theta of x is equal to theta 0 plus theta 1 multiplied by x. This x is just my single independent feature. Suppose if I have many independent features, it becomes a multiple linear regression. And with respect to this was the cost function that we used, right? The cost function was 1 by 2m summation of I is equal to 1 to m h theta of x of I minus y of I whole square. This h theta of x of I is basically my predicted point, and this is basically called as mean squared error. This is what is the cost function, mean squared error. And we also found out that whenever we try to plot our coefficient with j of theta, we were able to see something called as gradient descent. Our main aim is basically to come to this global minima. Okay. Now we are going to understand some series of algorithm which is called as ridge regression, lasso regression, and elastic net regression. And we'll try to understand why do we use ridge regression, lasso regression, and elastic regression. In this video, we are going to discuss just about ridge regression, and in the upcoming videos, we'll cover all the other algorithms. Now let's start with something called as ridge regression. So here I'm just going to write it down, which is called as ridge regression. Now let's say, guys, I have a single independent feature. Let's say I have something like x and y. Okay. And if I consider that I just have two specific data points in my training data set. Now in this particular scenario, obviously if I apply linear regression, this is going to pass through the best fit line. So when it is passing through, when I'm actually creating this best fit line, it passes through both these particular points, right? So this is my best fit line. Now when this is my best fit line, obviously you can see that the error is 0, right? Because there is no such difference, right, between the predicted and the real point. So in this particular scenario, I can definitely say this model is overfitting. Now what does model overfit basically mean? Okay, now with respect to this training data, you can see that the accuracy is very high. The error is very, very less, right? Or error is almost 0, right? But if I try to add some more new test data, let's say these are my new test data that I'm just going to add over here. Now when this new test data is basically getting added, you can see that now the error basically increases, right? The error with respect to this new test data is basically increasing. So this is basically a problem of overfitting. So here what is actually happening? Here overfitting is actually happening. Now what does overfitting basically mean? Because I have already covered this. Let's say with respect to our trained data, my accuracy is very, very high. Let's say my accuracy is 99% or 100%. Okay. And whenever I talk about trained data, at that point of time, we use something called as bias. In this scenario, I will be saying low bias. Okay. Similarly, with respect to the test data, when my accuracy is actually low, see, for the trained data the accuracy is high, but for the test data over here the accuracy is low. And in this scenario, whenever we use test data, here I am actually going to use something called as variance, and in this scenario it will be high variance. Okay, so this is the problem that is basically happening, right? It is overfitting in this scenario, right? Now how do I reduce this overfitting? I should definitely find out a way to reduce this overfitting, and for that specific scenario we use called as ridge regression. Because in this scenario I know my best fit line is passing through both the points. Okay, and always remember, guys, if you get an accuracy of 100%, right, definitely consider it that the model is overfitting. You should never get the training accuracy as 100%. Just imagine this. That basically means the model has been trained very well on the training data, right? Now let's understand what exactly ridge regression is all about. Okay, ridge regression is also called as something called as L2 regularization. L2 regularization, and this is used to reduce overfitting. Suppose my linear regression creates some overfitting, then in order to reduce that overfitting in the linear regression, we use ridge regression. Okay, so we can just consider ridge regression as a new algorithm which will actually help us to hyperparameter tune the linear regression. Okay, now let's go ahead and let's understand how does the cost function with respect to ridge regression look like. So here I'm just going to write down the cost function. Initially, if I consider the cost function of linear regression, I hope everybody knows 1 by 2m summation of I is equal to 1 to m h theta of x of I minus y of I whole square, right? So this is the cost function of the linear regression. Now in this particular case, see, when I create this best fit line, it automatically, passes through both the points in my training data. Now, when this is the scenario, obviously my entire cost function, this will become 0, right? Now, when it is becoming 0, that basically means my model is overfitted because it is passing through all the points perfectly. Now, in order to, remove or add some parameters, that we have to make sure that this never becomes 0. So what we do is that in ridge regression, we add two parameters. One is lambda, and the second one that we try to add is summation of I is equal to 1 to m slope square. Okay. So this lambda that you see is a kind of hyperparameter. Okay. And I'll try to show you the relationship between lambda and slope and how this is basically reducing the overfitting. That also we'll try to understand. Okay. Now, see over here. If I am trying to add lambda and slope square, let's say lambda value is 1. Okay. Now, when this value becomes 0, I have to make sure that this never becomes 0, because if this becomes 0, that basically means this best fit line perfectly passes through all the points, and this should not happen. So my cost function should definitely know that this is not 0 at this point of time. So what we do? We penalize this value by multiplying one lambda value. Lambda value I've just initialized as 1. Okay, and then I'll try to show you the relationship between lambda and slope. So after this one, let's say my slope, in this particular case, my h theta of x is nothing but theta 0 plus theta 1 x1. Okay, let's say I just have one input features. So summation of I is equal to 1 to m basically means how many number of coefficients or slopes are there. We are just going to do the summation of whole square like that. So here I'm just going to do theta 1 whole square. Now let's consider theta 1 any positive or negative value. Okay, so that basically means we are never going to get 0. We will be getting greater than 0, right? In this particular scenario, what will happen is that my model training, the best fit line will just not stop over here. Then it will try to find out another best fit line like this, or it will try to find out another best fit line like this, such that my cost function is minimal. Okay. So in this specific way, when I am specifically adding these two parameters, that is lambda and slope square, the situation is going to be in such a way that we are never going to get a best fit line that passes exactly through all the training data points. Okay. So this is how ridge regression is making sure that the overfitting will not happen. But one very important interview question that may come: what is the relationship between lambda and slope square? Okay. And for this, let's draw that same curve that we discussed, with respect to the simple linear regression. And this specific curve is with respect to theta, that is my slope, and cost function j of theta. Now, in this particular case, if you know that we will be getting this kind of gradient descent, right? Let's say I'm just going to put some points over here, like let's say this is 0, this is 0.2. This is 0.4, this is 0.6, this is 0.8, this is 1.0, and this is minus 0.2. Okay, let's say this I have just plotted with respect to theta and the cost function, okay, with respect to this gradient descent. Now just to understand, when lambda is equal to 0, see, when lambda is equal to 0, that basically means what? I will just have this same linear regression cost function. Okay, if lambda is equal to 0, this entire value will be 0. So that basically means I am not applying ridge regression over here. Whenever I apply ridge regression, I am basically using this equation at the end, right? So when lambda is equal to 0, I am just having this linear regression over here, the same cost function of the linear regression. This is fine. So this is basically my global minima, right? I hope this is my global minima. So let me say that, okay, this is my global minima. Okay, and this is when your lambda is equal to 0. Now let's say I increase my lambda to 10. Now what will happen is that I will get a new line which will look something like this. Okay, if you probably try to plot theta, I'm just trying to show you how the plotting, how the graph will look like when we increase our lambda. You can definitely check out by playing with different values. But once you increase the lambda value with respect to this theta, right, what will happen is that now this lambda value is basically getting assigned some value over here, that is 10. and when we multiply with the slope square, I will be getting a new gradient descent. And now you will be able to see that my global minima has changed. When my global minima has changed, so let me just draw this line properly so that you will be able to understand. So let's say my lambda is equal to 10. So what will happen is that when the lambda value increases, I will be getting another line which looks like this. So during when lambda is equal to 10, I'll be getting a different gradient descent. And now what is the difference between this gradient descent and this gradient descent? Here you can definitely see that my global minima has shifted. It has shifted from here to here, right? Similarly, my theta value has got reduced. Okay, it has basically shifted from here to here, right? This particular is with respect to this theta value. Now, similarly, if I keep on increasing my lambda value, let's say I increase my lambda value again. So with respect to lambda is equal to let's say 30, then I'll be getting another line which will look something like this. And now this will again get shifted. This global minimum will get again shifted somewhere here. So in short, what is happening? Theta value is again getting reduced. And like this, it will keep on happening. But always remember, in this particular scenario, it will never be 0. Okay? It will never be 0 as I keep on increasing the lambda value. So lambda over here can be considered as a hyperparameter. Okay? So lambda can be basically considered as a hyperparameter. And if you really want to know the relationship between lambda and slope, you can definitely say when lambda is increasing, your slope is decreasing. How slope is decreasing? Because we are going on this left hand side, right? You can see from 0.6 it became 0.4, 0.2, like this it is going on the left hand side. So this is the exact relationship between lambda and slope. But why we are trying to understand this particular relation? Let's say I have a multilinear regression. Okay, let's say I have a multilinear regression which is like this: theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. Let's say I have 3 coefficients and 3 independent features, and let's consider that theta 0 is equal to 0. If I say theta 0 is equal to 0, then what does this basically indicate? This basically indicates that it is passing through the origin, right? The specific line, this line is basically meeting the y-axis in the origin. This I have already discussed. Now let's consider that my theta 1 value, I'm assuming, okay, I got somewhere around 0.52 x1. I'm just assuming theta 1, theta 2, theta 3. Let's say over here I got probably 0.48, and here I got probably 0.24 x3, right? Suppose I got these values, and obviously I have theta 0 as 0. If I don't want to even take this, let's consider some different theta 0 value. So let's say this is 0.34. My intercept is 0.34. Now in this particular scenario, what will happen is that if I apply ridge regression on this cost function, then this value will get reduced. This coefficient will get reduced, but it will never be 0. See, what does this value basically indicate? 0.52 of x1. This basically indicates that with the unit movement in x1, right? With the unit movement in x1, what is the movement with y, right? So here you can see 0.52 movement with respect to y. Similarly, with the unit movement with x2, what is the unit movement with respect to y? So here you can see that it is 0.48 unit movement with respect to y. I'll not say unit movement, but 0.48 movement with respect to y. That basically means if x1 is moving by 1, then y will move by 0.52 in this particular case. If x2 is moving by 1, then 0.48 y will basically be moving, right? So this is what it basically indicates. Now, if there is too much movement, with respect to unit movement, if there is a unit movement, that basically means these features are highly correlated with the output feature, right? Highly correlated with the output feature. But here you can see that with respect to x3, we have a very small value 0.24, right? Even though we have a very small value, what will happen is that if I try to make a movement, unit movement with x3, there will be a small unit movement with respect to y, right? Somewhere around 0.24. But when I apply ridge regression to this equation, I may get something like this. See, I may get something like this, where this value will get reduced. This value will get reduced. Let's say it will get reduced to 0.40 x1. This may be 0.38 x2. But when I see this value will also get reduced, 0.14 x3. But here you can see that since this value has now a very small coefficient, this won't impact much change in the movement of this specific line. Okay? Because in this particular case, I have 3 coefficients. So this will then become a plane. This may become a plane entirely, right? The line that we are specifically using for division, right? So here you can see over here, since this value is very, very small, this won't impact the best fit line by a major movement. Only a smaller movement will basically happen. And always remember, this value will never become 0. That is what ridge regression basically does. And how it is reducing overfitting? Because it is reducing the impact by the coefficient, by reducing the coefficient of the feature that are not directly correlated with the output feature. Now here you can see x3 is hardly correlated by 0.24. And it is trying to reduce this particular value also. And when it reduces this particular value, that basically means this will not have much impact on the best fit line, right? So I hope you are able to understand. I hope you are able to understand the relationship between lambda and slope. So please just try to go through this video again. This all maths you really need to know, guys. Then only you'll be able to understand what things are actually happening. Now in the next video, we are basically going to discuss about something called as lasso regression. So right now we have completed ridge regression, and we'll try to understand what is the difference between ridge and lasso, and then finally we'll go with elastic net. Thank you.